Everybody, let's talk about transverse magnetic polarization in rectangular waveguides. Now remember, we did a very lengthy and detailed derivation for the transverse electric polarization, and we developed some very useful mathematical methods. But because we've already essentially done the work for the TE polarization, all of the exact same arguments apply for TM polarization. You just kind of have to replace E with H and apply a few of the appropriate constants of proportionality and coefficients along the way. So when we say TM polarization, what we're basically saying is the Z component of my H field is equal to 0. So there is no longitudinal component of propagation down my waveguide. And of course, we're also going to remember that all of my Z dependence is going to follow this e to the j beta z kind of function here. So let's go ahead. I'm going to write out my electric field profile. So remember, this is a function of x, y, and z. And for reference, we're going to write out the whole thing. So I'm going to get an x hat. I'm going to write this e sub x of x comma y. So I've taken away the z component here, plus e sub y of x comma y, plus z hat, e sub z of x comma y. And then all of my z dependence was factored out into this thing over here. So remember, we made this presumption that whatever my solution is inside of my waveguide, this is what the z dependence will look like. So I reduced my field components to this little e to kind of encapsulate that presumption. Likewise, my H field, and I can just put a R here sometimes instead of x comma y comma z, so that's a position vector. And then I will get an x hat H sub x of x comma y plus y hat H sub y of x comma y plus nothing. There is no z component to my H field, so I'm just going to leave that blank. And we get an e to the minus j beta z as well. Okay, so nothing here. That's what it means to be TM polarization. That little guy is 0. So just remember last time we used the HZ as kind of the anchor for our solution. So the exact same argument will apply in this case, only we're going to use the E sub z as our anchor here. So E sub z is our, I'll call it the anchor. And what that means is if I can solve for my E sub z, then there will be some quick little calculation I can do to get my other 4 field components. So we showed last time that the Hz would satisfy this kind of reduced 2-dimensional Helmholtz equation. And the same argument will apply. So what we're going to get is partial squared with respect to x squared plus partial squared with respect to y squared e sub z plus k naught squared minus beta squared e sub z is equal to 0. So if you're wondering where that came from, remember we did the exact same derivation for TE polarization and we got this exact expression only with HZ here instead of EZ. So the exact same argument will apply. We're just putting these EZs instead of the H. And of course, for convenience, this term here is given a name, k sub c squared, which is called the cutoff wave number, or the cutoff constant. So all we have to do is solve this equation here, and all of the other field components will follow. Because remember, E sub z is going to be little e sub z, my big E, is equal to this guy, e to the minus j beta z. So if I can calculate this thing, I just tag on that little z dependence to get my complete profile. And then likewise, we did this argument last time with the h's and e's, so now we're going to do this. If you apply the exact same reasoning, you get a very similar result, which we're just going to skip to the end, where h sub x is equal to j omega epsilon naught over k sub c squared times partial e sub z with respect to y. And then I'll have an e sub x here was equal to negative j beta over k sub c squared times my partial e sub z with respect to x. And then I had an h sub y is equal to negative j omega epsilon naught over k sub c squared partial e sub z with respect to x. So I apologize for being tedious, but there's a lot of things we got to calculate here. Negative j beta over k sub c squared partial e sub z with respect to y. So remember, the idea is if I can solve this equation and get some solution for my z component of my electric field, then I can use that to derive every other field profile using just some basic partial derivatives. So let's go ahead and do that now. Okay, so first things first, we are going to assume that my electric field, my z component, remember this is going to be a solution to my Helmholtz equation satisfying this thing here. So we're going to apply separation of variables again, and you can go through that whole process of calling it x sub x times y sub y, and you do the separation of variables, and you get that big long argument. And we already did that with the h field, so I'm just going to kind of skip a little bit to the end result, because the argument is exactly the same as before. We'll get something of the form cosine of k sub x x plus b sine k sub x x times this guy here, like c cosine k sub y y plus d sine of k sub y y. So again, if you are wondering where this came from, go back and watch the same derivation for TE polarization on the little hz here. And remember that in order to get here, we had to make the assumption that k naught squared is equal to k sub x squared plus k sub y squared plus k sub z squared, but we usually like to call that beta instead because it's special. Or you can also subtract here and get k naught squared minus beta squared is equal to our cutoff, kc squared, which is equal to kx squared plus k sub y squared. So remember, this stuff is imposed by the Helmholtz equation, and applying separation of variables to get this result, we have to make this assumption here. So we've skipped a little bit, but we've already done the math in a previous lecture, so that's okay. All we have to do now is apply boundary conditions, which in this case is actually very straightforward. We have the following boundary conditions: e sub z at 0, y is equal to 0. E sub z of a, y is equal to 0. So remember, this is just our tangential electric field must be 0. And we're just repeating it at the four edges of my waveguide. So e sub z of x, 0 is equal to 0. E sub z of x, b is equal to 0. So you notice it's the tangential. This e sub z is a tangential field to my rectangular waveguide. And it has to be 0 at all of my boundaries. So that gives me a nice straightforward boundary condition to apply. Whereas last time I had to calculate the E field out of the H field. Instead, I can just cut to the chase in this situation here. Okay, so we will go ahead and do that. Let's start with the first one. So E sub z of 0, y, just plug in 0 for x. And you notice this term goes away. That term becomes a 1. So we'll just get the following: a times 1 plus b times 0 times this stuff here, which doesn't matter, it's just some function of y here. And this is going to equal 0. So when you divide out everything, this all implies a has to be 0. Okay, because this thing is a function of y, it's just all of that. And I can divide it out, and this thing here disappears because it's 0. So you just get a equals 0 immediately out of that condition. So in other words, this guy here is not allowed in my solution because it will not satisfy this boundary condition. So let's now move ahead and do the same thing over here on condition number 3, where I get x, 0. The exact same argument applies. So this guy disappears, this guy turns to 1. This stuff won't matter because it's a function of x. So you basically get some function of x times c plus d times 0 is equal to 0. So the function of x won't matter. It disappears. That guy disappears. And so you eventually, you have to have the condition that c is equal to 0 in order for this to work. So that guy there disappears as well. So what we're left with then is the general solution e sub z is equal to a, or sorry, technically it's b, but I'm going to call it a now because it's arbitrary anyway. So I could have just as easily said ba. These are just labels. And we get a sine k sub x. Well, let's be consistent here. I'm going to call this b sine k sub x, and then I'm also going to get a d sine of k sub y. So the next step in the argument is to say, well, this is an arbitrary constant, and that's an arbitrary constant. So an arbitrary constant times an arbitrary constant is an arbitrary constant. So I'm just going to lump those together. Imagine they're like two blobs just smashing together to become a new separate blob. I'm going to call it a again. So I hope that's not confusing, but this is a common little thing to do with partial differential equations, is that these are all arbitrary constants, so I'm just going to keep calling it some kind of arbitrary constant here. K sub y, like that. So then you apply these next two conditions, and by now this process should start feeling a little familiar and tedious, where if I apply e sub z of a comma y is equal to 0, you basically get a sine of k sub x a sine of k sub y is equal to 0. So this stuff now divides out, and this guy has to satisfy the condition where k sub x is equal to m pi over a, where m is equal to 1, 2, 3, any positive integer here. So you notice 0 is not allowed, because if I put in a 0 here, I get kx is 0, and my general solution here becomes 0 as well. This guy here, I just get a 0, which is a trivial solution. 0 is out everything. So last time we were allowed to have a 0 mode. In the TE case, we are not, because the same thing will happen here when we do k sub y. So the exact same argument applies. You do the same thing again, n pi over b, where again n is 1, 2, 3. And again, the 0 is not allowed because these are sines now instead of cosines. So if I put a 0 here, it zeroes out everything and you get nothing, which is boring. A solution of all zeros is still a solution, but it's not an interesting solution. That's the trivial solution. So we just discard it as being uninteresting or unallowed in our final solutions. Okay, so then we'll just write out our general form here. I'm going to just move it up over here, where we get e sub z of x comma y is equal to a sine of m pi x over a, and then I'm going to get a sine of n pi y over b. So that is the general solution for my e sub z. Only not exactly, because remember, I can put in any arbitrary integer as I want for m and n, and those will also be solutions. So technically, I can add any of these together in any linear combination I like. So really, the general solution should look more like the following. X comma y is equal to a summation from n equals 1 to infinity and m equals 1 to infinity. Then I'm going to have the a sub mn coefficient, and then sine of m pi x over a. I'm sorry, I'm falling off the edge here. Let's see if I can squeeze it in here. Sine of n pi y over b. There you go. So that is the general solution for the z component of my electric field profile. And of course, because now I have these distinct set of solutions here, you get that same problem where beta sub n m, there isn't any one solution. This has to correspond to these other guys. So I'm going to write k naught squared minus m pi over a squared minus n pi over b squared, like so. Okay, and then of course we can apply a similar solution to my capital E sub z, and then from there we can calculate h sub x, h sub y, and then we can also calculate e sub x and e sub y by applying these expressions here. Okay, so once I have a solution for each little guy here, I can then create the full profile by tagging on this little bit here to get a full E sub z, and then all the rest are derived accordingly. So that's the idea of using this little guy as our anchor. Once I calculate this, everything else will follow. So that is the general solution. So just for completeness, I'm going to go ahead and add the z dependence over here just to reinforce that idea, where E sub z, I'm going to put a little r, so of x comma y comma z is equal to the summation over n and m, so same rules from 1 to infinity, a sub n m sine of m pi x over a sine of n pi y over b, and then e to the minus j beta sub n m times z. Okay. So that should look pretty familiar. You'll notice when we did TE polarization, these were both cosines. So now that we are in TM polarization, I get sine and sine. So for that reason, these zeros are not allowed over here, because any zero in here would zero out the entire field for that mode and make it uninteresting. Okay. So there you go. That is the anchored solution for the TM polarization in the rectangular waveguide from which we can then derive all other field components.